All right, so in this video, we're going to go through sample question 87 from the Society of Actuaries ExamP list of sample questions. The question reads, in an analysis of healthcare data, ages have been rounded to the nearest multiple of 5 years. The difference between the true age and the rounded age is assumed to be uniformly distributed on the interval from negative 2.5 years to 2.5 years. The healthcare data are based on a random sample of 48 people. Calculate the approximate probability that the mean of the rounded ages is within 0.25 years of the mean of the true ages. So, what kind of question are we dealing with? Basically, we're asked to find a probability. We're told we have a bunch of different items, 48, and we're told we need to calculate the probability of this average. So whenever we have this situation of, hey, we have a bunch of items, in this case, a bunch of people with ages, and they're identical to each other, they're independent, and we have a fair bit number of them. This is kind of lower than some of the previous examples you might have seen, but any number over 30 is kind of a go-to for central limit theorem. Okay, so we're going to use the central limit theorem to actually find this probability. Now, we're going to get into, in a sec, the difference between a total and an average. Some of the questions, if you're going through these practice questions in order, you would have just done a bunch of different central limit theorem problems, and maybe one of them, I believe, dealt with average. The rest of them dealt with totals. So there is a difference that's important to note later on. But for now, we need the actual information for the individuals first. Right? When it comes to central limit theorem, we're going to use a normal distribution. What's important for the normal distribution? Mean, standard deviation. We're going to need to find the mean and standard deviation of this mean of rounded ages. Okay? So let's just say the mean of rounded ages is x bar, right? So x is the difference in age. The mean of these differences, that's x bar. So we're looking for the probability that x bar is between 0.25 less than or equal to x bar less than or equal to 0.25. So in order to get the mean and standard deviation and variance and all that stuff for x bar, we need to know all that information for x. Okay, so we're told x is uniformly distributed. We need the mean of x. Luckily, we have something we should memorize, a formula. So the expected value of x, because it's uniformly distributed, is a plus b over 2. Upper bound plus the lower bound over 2. Negative 2.5 plus 2.5 is equal to 0. Divided by 2 is 0. Our expected value is just 0. The variance, however, is kind of a bit more, I'd say, annoying to remember. Right, where this is clearly just like an average sort of deal. This is the upper bound minus the lower bound, in parentheses, squared over 12. Okay, so this is equal to 2.5 minus negative 2.5 squared over 12. And that is equal to, give me a second, 2.5 minus negative 2.5, and I'm going to square that and put that all over 12. And I get 2.08, 3 repeating, so I'm going to round that, 2.083. All right, now how do we do that to get the variance of an average and the expected value of the average? Typically, when we use central limit theorem for the total, what we would do is simply just multiply each of these values by the number of items in our list. So the total would be 0 times 48, or here 2.083 times 48, and that would be good for total, not for the average. Here's what you got to know for the average. The expected value of x is going to be the same thing as the expected value of x bar. Your expected value is not going to change. So in this case, our mu value that we're going to be looking for, that we're going to be working with, is 0. Variance a little bit different. Be very careful. The variance of x bar is equal to the variance of x divided by n. Okay, so our sigma squared is equal to 2.083 over 48, the number of items we have. And then our sigma value would obviously be, let's see, let me divide this by 48 and then take the square root of that. A decimal that I would store in your calculator for when you do calculations of 0.2083. Oh, that's approximately, oh no, it's not, it's shifted decimal place. Okay, but you know, about correct answer. However, one thing I should mention, because I kind of just talked about it, when I'm writing stuff down and I'm rounding answers, when I actually do the computation, I'm not using the rounded answer that I wrote down, I'm using the value the calculator gives me. Okay, so now that we found the expected value and standard deviation, I can use the standard normal distribution. I'm going to calculate a z-score. And if you've seen a few of my videos, the z-score is x minus the expected value over my standard deviation. And I now look for, okay, what is the probability? Negative 0.25 less than or equal to x bar less than or equal to 0.25. And that is now the probability, negative 0.25 minus minus my expected value, which is 0, over 0.2083 less than x bar minus 0 over 0.2083 less than 0.25 minus x bar. Sorry, not minus x bar, minus 0 over 0.283. Okay, and I calculate this. So negative 2.5 divided by 0.2083, I get oh, hang on, missed the decimal place. There we go. Oh, 1.999 repeating. So I'm going to round that to a 1.2. Round to 2 decimal places when you're dealing with like using your normal table. 1.2, or sorry, negative 1.2 less than or equal to my z value less than or equal to positive 1.2. And what this means, right, a lot of the previous examples, with the exception of I think one, dealt with just like z greater than a number, z less than a number. Just to kind of do a little sketch, I think pictures are always helpful, is we have our normal distribution, something like that, perfect. And, you know, 0 is right here. And positive 1.2, let's say that's right there. Negative 1.2, right there. I am looking for the value in between here, the area in between these 2 points under the curve. Now, what the z table is actually going to get me is if I look up 1.2, I'm going to get the area of everything behind 1.2. If I use it for negative 1.2, I'll get everything behind negative 1.2. So the idea is, all right, let me actually get those values and take away all the area behind negative 1.2. Because that should leave me with the area in between these 2 points. And that's exactly what I'm going to do. I'm going to calculate a phi value for 1.2. And I'm also going to calculate a phi value. I'm going to subtract from it the phi value of negative 1.2. So going to our normal table. I look at positive 1.2, and that's 0.8849. 0.8849. Minus. Now, my table has it, your table will not have negative z values. So how do we actually calculate a negative z value? I'll go over it now because I don't think I've gone over it in other questions yet. So you can skip ahead a few seconds if this is something you definitely know how to do, but I do think it's good review. I got a z table, or not z table, a normal distribution, something like this, right? And let's say I want to calculate, oh, okay, this is a negative 1.2. I need all the things back here, but I don't have negative values on my z table. Since this is symmetric, if I find the z value for 1.2, right, the area under this entire curve is 1, and I find the area under this and subtract 1, I'll get this area, which will be the exact same as this area, okay? These two areas are the same. So, what I'm going to do is subtract away a 1 minus phi of 1.2, just like that. And what I should be left with is I'm going to distribute out this negative. I already know the phi of 1.2. I actually just calculated that to be 0.8849 minus 1 plus 0.8849. And just compute that. And I get a final answer of 0.7698. What does that line up with? Well, that lines up with answer choice D. Okay, so a few important takeaways from this problem. The main one being the difference between using central limit theorem to find a mean versus using central limit theorem to find information about a total. Okay. With a total, you could just multiply the number of items, there are n, by the individual expected value and variance to get the new expected value and variance. Here, you can't. For a mean, the original expected value for an individual is the same as the expected value for your average. The variance is equal to the original individual variance divided by the number of items there are. And other than that, it's pretty much just applying central limit theorem, calculating a z-score using the normal table. If there are any questions, anything you want me to clarify, leave it down in the comments. I'll answer to the best of my abilities. If this video helped you out, hit the like button and subscribe. That definitely helps me out. And if you want to see more videos like this, I got a playlist, Sample ExamP questions. Please go check that out. Hope you found this helpful. Thanks for watching.